Welcome to The Explainer. We hear a lot about AI being this jack of all trades. But what if you don't need a jack of all trades? What if you need a master? Today, we're going to dig into how you can take a super powerful AI and basically give it a specialized education, turning that broad knowledge into razor-sharp expertise.
Okay, let's just jump right in with a little challenge. So you take a general-purpose AI, right? And you show it this, a complex satellite image. What do you think it's actually seeing? I mean, yeah, it has access to a ton of information, but without specific training for this kind of thing, it's kind of like it sees the forest but misses all the important trees. And those are the details that can make or break a really important decision.
And right there, that's the core of what we call the generalist's dilemma. I mean, you can have the most powerful AI models on the planet, trained on, basically the entire internet. But that knowledge is often a mile wide and an inch deep. And when you get into these really specific niche areas, that lack of depth, well, it can lead to some mistakes that are honestly pretty basic.
So check this out. Researchers over at Mistral AI gave their base model, Pixtral, two images to look at. One of a playground, one of a stadium. And its label for both of them, stadium. Just stadium. The researchers pointed out that the AI completely missed the most obvious difference, the seats for spectators. To you and me, that's a tiny detail. But for the machine, it was a critical distinction it just couldn't make.
And look, this isn't just some abstract academic problem. The crucial thing to get here is that for really high-stakes stuff, we're talking climate science, agriculture, even defense, these small mistakes can have huge consequences. You absolutely need an AI that you can trust to tell the difference every single time.
But here's the good news. We don't have to go and build a brand new expert AI from the ground up every time we need one. There's a much, much smarter way to do this. It's all about taking that powerful, pre-existing foundation and just, very precisely, adding a new layer of expertise right on top.
And that solution is called fine-tuning. The best way to think about it is like this. You take a brilliant person who's had a great, broad education, and then you put them through something super focused, like med school or law school. You're not reteaching them everything. You're just adapting all that knowledge they already have for a very specific job. And the results, well, they can be pretty dramatic.
Now, the specific technique we're talking about here is called LoRA, which stands for Low Rank Adaptation. And honestly, it's incredibly clever. Instead of having to retrain the entire, massive model, which would take forever and cost a fortune, LoRA just injects these small, new layers. And those are the only parts that get trained. It's like giving a master chef one single new recipe to learn, instead of sending them all the way back to culinary school.
So the whole process is actually pretty straightforward. Step 1, you start with your powerful base model. Step 2, you inject these little trainable LoRA layers. Think of it like a little surgical procedure. And here's the key part. Step 3, you only train those new layers, and you do it using your new specialized data. And what do you get at the end? A brand new expert model, created in way less time and for way less money.
Okay, so that's the theory. But how well does it actually work in the real world? Let's take a look at the satellite test case where Mistral AI did this exact thing.
All right, so here's the setup for their experiment. They took their Pixtral 12B model. The data they used was the public aerial image dataset. And the task? Pretty simple on the surface. Classify thousands of images into 30 different categories. But the real challenge, as we saw before, was getting the AI to learn the difference between really similar things, like a playground and a stadium.
And yeah, the researchers themselves said it flat out. The base model, before any of this special training, just didn't have the context to see those little details that matter. This became the exact problem they were trying to fix.
But there was another pretty big problem with the base model. It had this tendency to, well, hallucinate. It would just invent labels that weren't even correct options. And this was happening about 5% of the time. Now, 5% might not sound like a lot, but for any serious application where you need to be able to trust the output, that's a completely unacceptable error rate. Okay, so that was our starting point. The generalist AI was, it was trying, but it was coming up short. The big question is, after this targeted LoRA training, just how much better did it actually get?
Well, the results were nothing short of dramatic. The base model's accuracy was sitting at just 56%. After fine-tuning, it rocketed up to 91%. That is a huge leap in performance. It literally transformed the model from a C student into an A+ expert.
To put that in other terms, the fine-tuned model was 1.6 times more effective at its job. Think about that. It went from getting just over half the answers right to getting almost all of them right. That right there, that's the power of specialization.
In this table, really, it tells the whole story. Accuracy skyrocketed to 91%. That hallucination rate, the measure of it just making stuff up, it plummeted to almost zero, 0.1%. But here's the number that's just jaw-dropping. The cost to get this massive boost in performance and reliability, it was less than $10. $10.
So obviously this is about way more than just telling stadiums apart from playgrounds. The real power here, the real takeaway, is thinking about how this same technique can be used in countless other super specialized fields.
I mean, just think about it. You could use this exact same method to train an AI to caption medical scans with like superhuman accuracy, or to read and transcribe fragile ancient manuscripts, or to sift through proprietary scientific data looking for a breakthrough. The potential here is just vast.
The researcher's conclusion really says it all, right? This approach gives you remarkable improvements, and it turns these big, general models into true specialists that are ready to go out and tackle very specific, very important real-world problems. And that really leaves us with a pretty fascinating final thought. When this kind of technology becomes this affordable and this effective, building a specialist AI is no longer a question of if we can do it, but of what should we do with it? What's the next big challenge we're going to solve?